Problem 5. This is a dimension analysis. So the question wants you to figure out, for part A, wants you to figure out the relationship between the heat loss H and the area of the fan, velocity of the fan, and the density of the coolant. The question wants you to find this function here. So usually the way you find out this relationship is to work to find the physics in it and to solve it. But right now you don't know anything about it, so dimension analysis is a good way to solve it. It does not work in all the cases, but so for simple cases like this, it works pretty good. So dimension analysis means you solve the problem using the units. So you want to look at the unit on the left side. Here the heat loss unit is watts. So this problem is not counted for the final score because it involves something you haven't learned yet, watts. Watts is the unit for power. And power is defined as energy provided per unit time. So 1 watts would be 1 joule per second. Joule is the unit for energy. Since power is energy per unit time, so 1 watt is 1 joules per second. And joule, if written in SI unit, written in kilogram, meters, and second, it would be kilogram meter squared per second cube. Okay. And this is also something you don't know. Oh, sorry. Square. But later you will learn this because energy, there are all kinds of energy. For example, kinetic energy is 1/2 mv squared. You can figure out the unit by using this formula. Here, this is in kilogram. Velocity is meter per second. If you square it, then it's this. Or you can use the potential energy for gravity, mgh. Here, m is mass in kilogram. G is an acceleration that's in meter per second squared. H is the height. Height is in meters, so kilogram meter squared per second squared. So now you know the unit on the left side of the equal sign, which is this. And then you need to know the unit for these 3 variables. First, for area, that's just meters squared. For velocity, it's meter per second. For density, density is a mass per unit volume. So it's a kilogram, unit for mass, divided by the unit for volume, which is meter cube. Now, you want to use these 3 guys to get this one. So this is like putting the pieces together, playing with Legos, using these 3 to build this. So let's see, how do you build this? First, you have kilogram here. The only part that has kilogram is the density. So you must have density, and it needs to be multiplied instead of divided by, because kilogram here is in the numerator, and here is also in numerator. So first we must have density here. Now here the unit is kilogram per meter cubed. Next, meter squared. Okay, so which piece has meter? All of them has meter, so it's unclear which to use. So let's skip this and look at the next one, second. So second squared, only velocity has second, so we must use velocity to get this part. And since it's squared, so we must, oh, this is joule. This is joule. For watts, is joule per second. This would be cube. So we need, instead of cube, we need, instead of square, we need cube because it's not joule we want, it's watts we want. So we need velocity to be cubed and also multiplied by, because here second is in the denominator and here also in denominator. So we must have velocity Q. Then if you cube the velocity here, that's meter per second cube. Then you can see that these guys cancel out. Then if you compare this with the final result we want, the only thing we're missing is a meter squared, which is exactly the area. So just put an area here, and this is what we want, kilogram meter per second cube. So this is really what we're looking for. That's part A. It involves something you haven't learned yet, the unit for energy and power. Now, if you know the formula from part A, part B and part C, you should be able to solve it with the knowledge that have been covered in the lecture already. So, part B, remember I have here, so the original heat loss is 230 watts. Now to increase the speed 4.5 times larger. So that means velocity changes from the original value, v, we don't know what, but it changes from this value to 4.5 times larger. And density of the coolant is 7.5 times smaller. So if it's 7.5 times smaller, it will become 1 over 7.5 of the original value. Now, how would this change? The heat loss change. So now velocity increased. If we look at the formula, H equals rho A V cubed. Here, velocity is cubed. So if it's 4.5 times larger, then H will be 4.5 cubed times larger. And rho here is also multiplied with the rest. So if the density is 7.5 times smaller, then this would just also be 7.5 times smaller. So H will change from the original value to this value. Then just this gives the result is 12.15, and just times your original power heat loss. So this is how I solve part B. Part C is similar, but kind of backwards. So in part C, you want to keep the heat loss the same. And you decrease the velocity reduce the speed by a factor of 2.5. So if velocity is to be reduced by a factor of 2.5, then H would also be reduced 2.5 cubed times smaller. And now how should we increase the area to make the heat loss stay the same? If it stays same, which means H changed from H to H again, this part should be 1. So let's say we increased the area x times larger, then H would also increase x times larger. Then if we want H to remain the same, then this should just equal to H, which means x divided by 2.5 Q should be 1. X is just 2.5 Q. This is part C. Question 6. man's blood pressure is measured to be this value, 1.119 plus minus 2 millimeter mercury. This is just a unit of the pressure. So what's the uncertainty percentage? If it's just the uncertainty part, 2 millimeter mercury divided by the measure value 119 times 100%. Give you part B. If this uncertainty stays the same, for measure result 79 millimeter mercury, what would be the uncertainty? What would the uncertainty be? Well, you just multiply with the uncertainty level you just calculated. To give you. Not much to talk about this one. Next one. Okay, next one is about significant digits. So how to count significant digits? Let's use an example. When you count significant digits, you always start from the first non-zero digit. So for example here, 0, 0, 0, these three just doesn't count because they are both zero, they are all zero. You start from the first non-zero digit here, 1, then you count all the way to the end. If the number contains a decimal point, you count all the way to the end. 2, 3, 4. Now it's very important you include these. They also contribute to the significance. And you want to exclude these non-zero part. Now another example would be this. Start from the first non-zero, 1, 2, 3, 4. Wait, if there's a decimal point. Okay. Now if there's not a decimal point, just this, then you should again start from the first non-zero, then count to here, then you end. These you don't count because there is not a decimal point. Okay. Now part A, we have a number 8.3 with a bunch of zeros, millimeter. We want to write it, report it as three significant digits. So count from here, 1, 2, 3. This is all we need. 8.30. Part B, because this involves calculation. Now, when you're multiplying and dividing, you want to keep your result the same as the significant digits of your result should be the same as the input values with this significant digits. For example, this one, 1.81 meters per second squared. This one has 2 significant digits. This one has 3. So your result, if you calculate it, the value is 147.15. But you want to report it with only 2 significant digits. Okay? Because this one is not accurate enough. You only have 2 significant digits. So you want to report this with only 2 significant digits, it would be just this 2. And this should be this 4 should be rounded up into 5 because this is 7. So 150 kilogram meter per second squared. Next one is 15.6. Centimeters minus 2.6 millimeters. Okay, first thing you want to notice is the units are different. So when you calculate, you have to convert it first. Second thing is, when doing subtracting and adding, you should keep the same decimal place. Okay? So what I mean is, let's first do the conversion. This is, okay. Now, if you calculate it, it would be this, but you want to report it as 15.3 centimeter. Because this is only accurate to the one digit after the decimal.